Okay, suppose I have a particle that has a mass of m, and this particle is moving on this kind of frictionless surface from here to there. Okay? The force acting on this particle from this state to that state, in this case, is only gravitational force. Right? 이민우? Huh? Other force you can imagine? Okay, if it is not frictionless, there will be this force as well as some force tangential to the surface. Okay? So what if there is a friction force? That means I am moving this on this kind of surface, Okay? What happened using principle of work done and kinetic energy? Then U12 has two contributions. One is due to gravitational force. The other one is due to friction force. What is it? The work done due to gravitational force is mg y2 minus y1, that I'm saying this is y. And this is y1, and this is y2. Is this correct? Why not? Because this simply says integration from 1 to 2. The force is mg. If I use the unit vector in this direction, j, then that is mgj from the r. In this case, this is y j vector, right? Because dr vector, in this case, dyj vector, right? Right? Therefore, the result is y2 minus y1. Correct? Okay. Because I'm using the coordinate like this, the force has to be mg, j, but has a negative sign because of the sign convention I use. Okay, this explicitly shows if you follow the definition of work done using coordinate, again you have to follow the sign convention of coordinate. But if you just use the concept of work done that says the force multiplied by the amount of displacement that has been increased, then you can just say mgh. But I recommend you to use this approach in the beginning until you have a solid idea to avoid any mistake. So this has to be y1 minus y2. So we are happy to obtain the height of h. Okay? Now, if this one moved from to here, following this kind of path, this definition of work done says that Doesn't matter whether this follows this path or that path. Again, if this one comes from this one state 1 to state 2, and if it moves back to state 1, in other words, work done, completing one cycle, this kind of force, mgh force, this one followed here and then back here, what is it? The work done is 0. Okay, work done is 0 due to gravitational force. The force follow this kind of, the property we call this is conservative force. Typical example is gravitational force. And if you look at this formula in detail, that means mgy1 minus mgy2. And this called potential energy due to gravitational force. And we denote that is V1 minus V2. Okay. So if we are handling the force that has this kind of property, for example, there is another force that follows that kind of property. For example, if there is a spring, and I elongate it, and I release it, then the force acting on this string is F, that is proportional to the displacement, and we call F equal Kx. Okay, the amount of this displacement which I am producing using Fx is x. Then Fx multiplied by x. Okay, that kind of force multiplied by x is Kx dx. Therefore, that is the change of 1/2 Kx squared, right? I'm saying that work done due to spring is equal to F is Kx multiplied by dx, and that is integration d 1/2 Kx squared, right? Therefore, that is 1/2 Kx 1 to 2 Kx 2 squared minus 1/2 Kx 1 squared. That is correct? Huh? Where the minus has to do? Here? Okay. He is correct. The reason why there is a minus Kx, if you look at free body diagram of this string, okay, and this is the force, directional force. Okay? Therefore, that has to be minus. Therefore, I got minus over here. Therefore, I have over Kx1 minus Kx2. Again, that is V1 minus V2. So spring force also can be regarded as a conservative force. So in this case, we can say for the special case, for the special case, work done is equal to change of two potential energy from 1 to 2. Note that this is not V2 minus V1 for conservative force. Okay. And we also know that work done will change the kinetic energy. Therefore, we can say T1 plus V1 is equal to T2 plus V2. This is total energy, and this is total energy at state 2, and we say energy is conserved. Okay. But if we have a friction, the work done due to friction will change our result. Okay, work done due to friction is the friction force multiplied by the path S from here to there. Okay, in this case, work done from 1 to 2 is equal to V1 minus V2 plus work done due to friction, that is friction force multiplied by the distance S. Okay? So in this case, this would not hold, right? Because the force we are considering is no longer conservative force. Now, let's go back to the famous pendulum. Okay, from here to there, at this state, what kind of energy you can imagine? One is potential energy due to the presence of gravitational force field, that is mgh, if you have a datum of potential energy from this position. Okay, and this is h. If you have a datum from that position, then the potential energy would be mgh plus this distance. Okay, now when it passes over here, and no kinetic energy because I'm holding this, and when it passes over here, the potential energy of this particle when it passes over here would be mg multiplied by this amount, right? Plus kinetic energy. But because you have the same potential energy due to this distance, you don't have to, have a datum over here. I mean, it's not necessary. You just have a datum over here. Then you could say the potential energy at this point would be mgh, and over here there is no potential energy if I take a datum over here. And that is 1/2 mv